Problem F7-5. Determine the normal force, shear force, and moment at point C. So, in order to find these internal forces, we first need to know all of the applied forces. We have this distributed force right here that peaks at 9 kilonewtons per meter, but we also have a reaction force at A and a reaction force at B. The reaction force at A is a pin reaction, which means it could have a horizontal component and a vertical component. And the support at B is a roller support, meaning it only has a vertical component. In the horizontal direction, this is easy. The only force acting in the horizontal direction is the reaction at A, so the horizontal component of the reaction of A is 0. In the vertical direction, we have the reaction at A upward and the reaction at B upward, but we also have this distributed force downward. Now, there are two ways we could deal with this distributed force. The first way is we could define this W function and then say that the net force is equal to the integral of W of x dx, and the net moment is equal to the integral of x W of x dx. So this is a linear, for this segment, the W function is linear, is proportional to x, starts at 0, peaks at 9 kilonewtons per meter at 3 meters. So for that first section, W of x is 3 kilonewtons per meter squared times x. The second function doing the same thing, we know it's 9 kilonewtons per meter at x equals 3 and 0 at x equals 6. That gives us a W function of 18 kilonewtons per meter minus 3 kilonewton per meter squared x for that range. But I'm not going to do it this way. I'm going to do it a slightly easier way, and one that depends on the geometry of the problem involved. The net force is equal to the integral of this W function, but on a graph, integral can be found as the area under the curve. This curve is a triangle. The area of a triangle is 1/2 base times height. The base is 6 meters. The height is 9 kilonewtons per meter. So 1/2 times 6 meters times 9 kilonewtons per meter is 27 kilonewtons. We can also look at this distributed force, see that it is symmetric about this point in the middle, and say that it acts at x equals 3 meters. So to find the reaction forces, we will use Newton's second law. In the y direction, there is the reaction at A plus the reaction at B minus that 27 kilonewtons of equivalent force equals 0. And for moment, I have selected moment about point A. So the reaction force at A will not create any moment. This distributed force will act as a 27 kilonewton force located here at 3 meters. So, and it would cause a clockwise rotation about point A, so it's in the negative direction. So negative 3 meters times 27 kilonewtons. Then the reaction at B, it's 6 meters away from A, and a positive reaction force at B would cause counterclockwise rotation, so positive moment. So plus 6 meters times RB equals 0. To solve these two equations, we get RA is equal to 13.5 kilonewtons and RB is equal to 13.5 kilonewtons. Now, because this happened with the other problem, I should emphasize the two reaction forces are not always going to be equal. It is something of a coincidence that the two problems I selected, they are. Although in this problem, we can see that there is a symmetry to this problem. There's a reaction force at this end, there's a reaction force at this end, and there is a symmetric distributed force throughout the beam. It does seem reasonable that these two reaction forces will be equal. Just keep in mind that's not always the case. So next thing we're going to do is we are going to cut this beam at point C. And I'm going to look, and I've selected to look at the left half. Now, when we cut the beam, we also cut the distributed force. Instead of a 6 meter across 9 kilonewton per meter peak triangle force. We have a 3 meter across 9 kilonewton per meter peak triangle force. That's also one that's not symmetric. So we cannot use F is equal to 27 kilonewtons located at x equals 3 meters anymore. Now we could still do this kind of geometric calculation. We could say this is still a triangle, so 3 meters by 9 kilonewtons per meter times 1/2 because it's a triangle gives us 13.5 kilonewtons. And we could say that because it's linear, it's located 2/3 of the way from the zero end, so it's located at x equals 2 meters. We could do this, but I'm going to do it the hard way this time to show you how it's done. Fortunately, we already have the w function. We found that right here, and that is still the same w function. This is the part that got cut off. So w of x is equal to 3 kilonewton per meter squared times x. So for sum of forces, we have the reaction at A upward. We have the negative integral of the w function. So negative integral, this is w, 3 kilonewtons per meter squared x, dx, and we put in our bounds as starting at 0 and ending at 3 meters. Lastly, there is the internal shear force at C, and let's check our sign convention again. On the right-hand side, internal shear is downward, so minus V of C, and set that all equals to 0. Now let's plug in some numbers. R of A we already calculated as 13.5 kilonewtons. This integral right here, it's 3 times x, so the integral of that is 1/2 times 3 times x squared, because remember, this is x to the first power, becomes x to the second power, bring the 2 down. So the indefinite integral of 3x dx is 1.5 x squared. Next, we put in our bounds and integration, and I apologize for this notation. I could not do two numbers vertically in this document, so try to keep in mind that this is our bounds of 3 meters and 0. So we plug in 3 meters for x, we get 1.5 times 3 squared, that's 13.5. Plug in 0, 1.5 times 0 squared is 0. So this integral, or this evaluation of the integral right here is 13.5 kilonewtons, which means easily V of C is 0. The internal shear at this point is 0. Next, sum of moments. So again, I have selected to take my sum of moments about point A. So the reaction at A will not create any moment. The reaction due to the distributed force is the integral of x times w of x. So remember, w of x was 3 kilonewton per meter squared x. So x times w of x is 3 kilonewton per meter squared times x squared. And integrating that with respect to x from 0 to 3 meters. Plus the moment at C, again, on the right-hand side, internal moment is positive. And again, minus the moment resulting from the shear at C. But since the shear at C is 0, this will go away. Evaluating this integral, the integral of 3x squared dx, the indefinite integral is x squared becomes x cubed, bring the 3 down, that becomes 1x cubed, evaluated from 0 to 3 meters. Plug in 3 meters to x here and you get 27 kilonewton meters. Plug in 0 to x, you get 0. So this evaluates to 27 kilonewton meters. 27 kilonewton meters plus internal moment at C minus 3 meters times 0 is 0. That gives us internal shear at C is 0. Internal moment at C is negative 27 kilonewton meters. Apologies for the jump. I realized that I had made a slight mistake. on this segment, this distributed force about point A will create a clockwise rotation, which means the moment here should have been negative. So negative moment there, which would make the internal moment at C a positive 27 kilonewton meters. And once again, there are no forces in the x direction, so the internal normal force is 0.